And presenter.
Yeah. So let's see. Okay, here it is. Okay. Okay. Hello, everybody. I'm Alberto Garoffolo. I'm head of ZK at Telos, and today I'm going to present to you SNARKs, a decentralized protocol for scaling zero-knowledge proof verification on chain. So let's start from our first consideration. Currently, just a small part of the real-world use cases are on blockchain. And what are the main reasons? I mean, for sure, you know, scalability and fees are two things that are connected because you have, let me say, limited resources, and these lead to high fees. And high fees, let me say, prevents many use cases that cannot afford these fees. But there are other reasons for limiting the mass adoption of blockchain. And one of these is the lack of user data protection. So what do I mean here? Currently, if you want to have an on-chain application, all the data that need to be verified on-chain has to be on-chain. So if you want to build an application and you want to verify some statements, you have to oblige the user sharing all this data on-chain. And if we take as an example a car rental application, a very simple example, we can expect that the user should provide at some point that he has a valid driving license. But currently, in the current architecture, this means the user having to share his driving license information on chain. And obviously, this is something that you would never do. You would never share your driving license data with everybody for the rest of your life. And one other important limitation that we have right now is an increasing need for compliance with government rules. And what do I mean here? Let's again take another example. For example, if we want to implement a casino game application where the developer wants to be sure that the user is over a certain age. Otherwise, I mean, it would be illegal in many countries. And so also in this case, the user has to share his digital identity information on chain, and obviously this is not acceptable. And last but not least, interoperability. Currently, we have a scenario that is very fragmented where you have many layer ones, many layer twos, and they are not able to communicate together in a trustless way and secure way. You are always trusting someone in some way or another, and this is, let me say, preventing also a mass adoption of blockchain. So now let's see how ZK SNARK can play a role in solving all these issues. Okay, for example, scalability. We all know about ZK rollups. I mean, with ZK rollups, you can, by adopting SNARKs, you can enable fully trustless and secure bridges with layer ones, because you're able to prove the state of the layer two, and so you're able to prove to the layer one what's happened on the layer two, and so you can see SNARK how it's fundamental. And then we have, for what regards user data protection, with ZK SNARK, you can allow the on-chain logic to verify statements on user data without having the data. So the user can provide a zero-knowledge proof about some statement on his data, and he will share the zero-knowledge proof on-chain and not the data itself. Going back to the car rental example. I can prove that I have a valid driving license without having to give you my driving license. And so this means that you can write an on-chain application that doesn't require you to share your driving license. You share the proof that you have a valid driving license. And so we solve the problem of user data protection in this way. And the third one, for what regards compliance, if we go back again to the example, in the casino game application, instead of sharing my digital identity, I can share a proof, a zero-knowledge proof that is a cryptographic proof that says I'm over 18. And again, I'm not leaking data, or better, the user is not leaking data about his digital identity. And last but not least, for what regards interoperability, again here, we can leverage SNARKs and recursive SNARKs to succinctly prove the state of a chain. And this is something similar to what Mina does. And so if you have a succinct proof of the state of the chain, you can prove to another chain some facts about the source chain. So you just share the zero knowledge proof, and you can convince the other chain about facts that happen on the source chain. And so you can enable fully trustless and secure communication between chains. So now we saw how SNARKs and ZK SNARKs can solve these issues, but now we have a problem, because if you start thinking in this direction, you can see that in the future we can have, let me say, most of the transaction that will leverage zero knowledge proofs. But now you have all these transactions that needs to be verified on chain with that zero knowledge proof. And so what will happen? That the network throughput will be heavily influenced by the efficiency in verifying the zero knowledge proofs. And even currently with the most efficient proving systems, let me say, zero knowledge proof verification can take a substantial portion of the computational budget of a transaction or of a block. And the situation is even worse if you want to provide to the developer a good user experience. And here what I'm saying, there are ways for generating, for verifying and generating proof of statements on some data that leverage the possibility to use for the developer a common, let me say, high-level language, like for example Rust. But this implies using zero-knowledge virtual machine that usually requires some proving systems that have, let me say, are less efficient in terms of verification. So the situation can be even worse. Obviously, you can think about using proof wrapping in order to change, I'm simplifying here, change the proving system, okay, in order to end up with a proving system that is more efficient in verification. But these introduces additional latency, is very computationally expensive, introduces additional latency, and these, let me say, prevent many use cases, because if you introduce too much latency, the use case will not be possible anymore. So, and last but not least, proof verification can be a completely stateless task, but if you do it on chain, it will consume stateful resources. And so we're using the most scarce resources for verifying something that can be stateless. Here in this scheme, we can see what I just described. You can have several users that are generating a proof of some statements on their private data with the prover, and they are generating the proof. And then they are creating this transaction that leverages the proof, and this transaction has to be sent on chain. So, for example, this would be the transaction that says, I want to rent a car, I have a valid driving license, here's the proof that I have a valid driving license. And then you can have, for example, several rollups that all of them want to roll up on the layer 1. And also in this case, you will end up with having many transactions, all of them with a zero knowledge proof, the SNARK proof. And so now you can see that how big is the issue if you are not efficient in verifying the zero knowledge proof on chain, whatever it is, a layer 1 or a layer 2. Okay, so now we can see how can we design SNARTR in order to enable efficient SNARK verification on chain. So what is the main principle? Having one unique proof that validates many proof. So with SNARTR, we leverage recursive proof composition in order to end up with a unique proof that validates many proof. So on chain, we send just one proof that validates all the underlying proofs, instead of having all the proofs included in the block, for example. We can see here in the scheme, instead of having all the 4 proofs, we have just one proof there, the P AG14 that is the result of the aggregation of the other proofs and is a cryptographic proof. So you're not trusting anybody. It's fully trustless. So, and what is the characteristic of PAG14? The verification time of it is constant and is independent of on the underlying proofs. And so you can see how you can scale in this way. Okay, going on with the main principle is that the protocol has been designed in order to be decentralized. And why it's important? Okay, now we are in the scenario where you have several transactions, all of them with zero knowledge proof, and then you have a protocol that is aggregating them. But then, if this protocol is centralized, what you will have, these who is running this protocol will be able to censor all the transactions. So it's important that the protocol itself is decentralized. Otherwise, it will become a big threat in terms of centralization and in terms of functioning of the underlying blockchain. So one other element is obviously the scalability. So we designed the protocol in a way that both the proof aggregation and proof verification can be parallelized. And we will later look into more details about the verification part. And obviously, if it is decentralized, it needs to have a proper incentive scheme that lead to fair fees for the user, but also fair rewards for all the actors that are involved in the protocol. Okay. Here it is. Okay, now let's see very high level how it works, the protocol. The user will submit the proof along with an aggregation request to the SNARK or decentralized network. And the SNARK or decentralized network run the aggregation protocol that continuously process the proof by aggregating them. And the protocol also periodically submits the proof, let's say, the best proof, and we will see later what do I mean here, on chain for verification. And then the proof that has been submitted on chain, the aggregated proof that has been submitted on chain, allows the user to prove that he had a valid proof. So you submit the protocol submit the aggregated proof. The user then submits a transaction that says, okay, the aggregated proof proven that I had a valid proof, so I had a valid driving license. Okay, here we can see what I just described. You have the rollups, the users, they are generating the proofs, they are submitting the proof to the SNARK or decentralized network, where happens the aggregation process, and then periodically one proof is submitted on chain, and then users and rollups can submit the transaction that is referring to the aggregated proof. So you can see now that we just include one proof instead of many proofs, and we are achieving the same result. Here we can see the same thing from another perspective. You have several users, several rollups. They are sending the base proof, and then you have the aggregated proofs that recursively merge the base proofs, and you end up with a unique proof. In this case, it's called AgProof 1M, and this one proof is included on chain. And then you can include the transactions that are referring to this aggregated proof. Okay, now let's see who are the actors involved in the protocol. Okay, the users, we just saw what they're doing. So they submit the aggregation request and then the actual transaction referring to aggregated proof. And then we have schedulers that are entities that are coordinating the proof aggregation work. So they're responsible for assigning the proof aggregation work to other entities that are called provers. And then the provers are the actual worker that perform the proof aggregation according to the schedule provided by the schedulers. And then you have submitters that are the actors that are responsible for picking up one aggregated proof and submitting on chain. And depending on the implementation, you can select both submitters and schedulers from the block producers of the underlying chain. In such a way, you can inherit some of the assumption in terms of the decentralization of the underlying chain, and the incentives are aligned. Okay, let's go a little bit more into details about the flow. So the protocol operates in an environment where the time is divided in time slots of constant duration, and each of these time slots is assigned to a proof scheduler. Meanwhile, users are sending their request for aggregation of their proofs, and now you have these schedulers that are keeping, that are assigned to each slot, and they are keeping a queue of proofs. And so they consume the proof queue and they issue a schedule defining which prover has to work on which couple of proofs. And then each assigned prover then merge the assigned proofs and share it back to the schedulers. And so the next scheduler will be able to generate a new schedule by removing from the queue the source aggregated proof, adding the aggregated proof, and adding the newly arrived proof from the users. And this process continues, let me say, infinitely. And then what happens is that the schedule loop goes on. Here we can see the what I just described. So you can see on the bottom the slots, slot 1, 2, 3, and 4. And then the slots are assigned to schedulers. The proof of the users are coming, and the scheduler is issuing a schedule. In this case, the first schedule says, okay, P1 base and P2 base has to be merged by prover 1, P3 base, P4 base by prover 2, and so on. So the provers start generating the proofs. The queues are updated of the schedulers, and then the next scheduler, the scheduler 2, will issue a new schedule that now will say, okay, prover 1, aggregate these two proofs that are not anymore base but are aggregated proofs that are P12 and P34. And so you can see that the tree of proof is building, and this loop continues infinitely. So now let's see the submission flow. So as we said, the submission flow is responsible for picking up the best proof, the merged best proof, and why it's important that is the best proof. And for best, I mean the one that aggregates more proof, because this allows to have a higher throughput, because unlocks more transactions that now are able to go on chain and say, yeah, I had a valid proof. Okay, and so and here the submission environment is divided in epoch, in submission epoch, that depending on implementation, but usually can be bound to blocks, chain blocks. And each submission epoch is assigned to a specific submitter, and then the assigned submitter takes one of the aggregated proofs, finalize it for submission, and then send it on chain. Here we can say that the previous graph, just with the light blue parts that are the proof that are picked up by the submitter and then submitted on chain. Okay. Previously, I mentioned about the verification of the proof and the possibility of parallelize the verification. Okay, let's say in P2P networks, it's very common to have the requirement of verifying each message before being broadcasted to other participants. Why? Because we want to prevent DDoS attacks, and we want to prevent the possibility for a malicious actor to flood the network with invalid messages. Okay, in our scenario, you can see that we are sharing proofs among the network participants. And so now we have the requirement of having, for example, the scheduler verifying all the proofs before assigning them. And this is another bottleneck. And we want to remove also this bottleneck. Okay, so what we are doing for removing this bottleneck? We let me say, set this requirement only for the prover. So the assigned prover is the only actor responsible for verifying the proofs, even in primitive. But now we have a problem because you can flood the network with invalid proofs. But the prover has the possibility, so we created the possibility for the prover to creating a proof of misbehavior that is a cryptographic proof of misbehavior. So we created a SNARK that allows you to prove that there was an invalid proof. So the prover is proving that the user sent an invalid proof. And this proof of invalidity is included as well as any other proof in the aggregation process. And when the aggregated proof goes on chain, it will be possible then to bill the malicious actor for the proving cost, for the misbehaving proving cost. In such a way, you can see that we removed the need for the protocol participants to verify the proof in the gossiping protocol, but we still are protecting the network from DDoS attacks because we have a way for making this attack very costly, and in any case will not create any damage to the network because every actor will be rewarded for the work of proving the misbehavior of the bad participant. Okay, and so just a few conclusions here. So we saw how SNARKs will play a fundamental role for enabling many use cases that currently are not possible, are not there. And then we saw then the problem that arises that ZK SNARK verification will be the next bottleneck. And so we need to have a way for verifying zero-knowledge proof in a very efficient way and not spending stateful computational resources. And then we saw how with Snarktor we designed the protocol in order to massively scale user SNARKs proofs and also rollups proof in order to have, let me say, faster proof verification in a totally decentralized and trustless way. And that's pretty all. And so, I mean, there is a white paper that goes into details about more details about the protocol that I just described. And if you want to have a look, here is the link. Thank you, everybody.
Thank you very much. We have some time for maybe one question, if there are any. Okay. I guess everything was perfectly clear. Well, thank you very much once again.